If I say something wrong, you can correct me. So first, before we build FFT, we have to build up a group. We choose a group of p equals to 31. And you can see my code in Zoom. So we had to understand that we choose actually the group is fp squared. And p equals to 31. And we let G equals to the generator of the fp square to the F31's order minus 1. This order is yes. And to check the order of G, we define the function group odd. And as we can see, the order of G is 32. So yes. And it is because that of this formula, p squared minus 1, it leads to the p squared minus 1, p plus 1 multiplied p minus 1. And this is p minus 1, so G to 32 is 1. And also we define some operations on this group, like group 8. Okay. And
This is add or multiplication or multiply?
This. Oh.
Or it is the only operation on the group?
Yes,
So it's
yes,
data.
yes. Um, so we can define a group G5. So this is the group that we want to use in so-called FFT. And we can print the group, as you can see in Zoom. And we can check that that 1 in G5 multiply 1 in G5 equals to 2 in G5. And I think we can skip this part. Let's see the FFT function. So at first we randomly choose f, use random int function, and you can see the f here. And then we define the first step of circle FFT, which is a little different from later steps. First.
So you do the FFT on the G5 or the coset of G5?
Actually, on G5 now.
If you do FFT on the G5 in the first step, the inverse of the unit element is itself, so it's not a 2-to-1 map.
Yeah.
So you need to do the FFT on the coset of the subgroup.
Okay. Okay. Oh, okay. Okay, so we do FFT on the coset of G5. And the normal step, we also have to define a normal step. Which is a little different from first step. And also, you have to mention that if y is equal to 0, else 0. Also this part. Okay. And so the total process of FFT is to call the first step function at first. And then apply F0 and F1 to a recursive function. Yes, and finally, calculate FT.
我说那个对应状的话也可以不用写，大家都可看着。
嗯。Yes, basically, the code is as follows.
Is this FFT from original paper or other blog? Because you have a case of y equal to 0, but y equal to 0 is an element of subgroup. It's not. If you only consider the coset, they are not a case of y equal to 0.
Okay.
So it may be another method to do the FFT on the directly on the subgroup.
Maybe I
think just because he doesn't care about the high X projection part, so
Yeah.
literally the FFT is over the complex field. I think I'm not sure. I haven't seen the code.
So the first step, there's a case of y equal to 0. So this FFT can be due on the subgroup directly, right?
Yeah, I think.
Yeah. So it's not. It's different from the original paper.
Yeah.
yeah, maybe because I haven't chosen a coset.
Yeah.
Yeah. Okay. And I haven't figured out how IFFT is implemented.
It's like the same as FFT, but you do everything backwards.
Okay. Thank you.
Yeah, but basically, yeah, okay, so the way IFFTs always work, right, is, so for an FFT, you have like log n steps, right? And you have like step 1, 2, 3, 4, 5. And then at every step, you have like some F0 and then F1. And basically what you do is this is like a vector, and then you multiply it by some matrix, and then that equals like output 0, output 1, right?
Yeah.
So like over here, maybe like the matrix might be like 1, 1, 1, negative 1, or like sometimes something else. Right? And so to do it to do it backwards, you do O0, O1 times matrix minus 1 equals F0, F1. So you just calculate what this matrix is, and then you just do the same thing.
Okay.
Yeah.
Understand.
And then the inverse of the matrix is also a Wendland matrix.
Sure, yeah.
So later we can use the same recursion structure.
Yeah, you can use the same structure because it's just like what you do is you just take the same code as an FFT and you just like reverse order everything and you replace that with the inverse of that.
Okay, thank you.